All right, today we're going to revisit limits, and in particular some of the forms of the limits that we run into that we didn't know what to do before. We had our techniques of solving limits, but now we're going to look at some different expressions that we're going to try to solve. In particular, if you look at the two examples that are on the screen, when we solve limits to begin with, the first thing we try to do is direct substitution. So on that first one, the limit as x approaches -1 of 2x squared minus 2 divided by x plus 1, we could try to go with a direct substitution. Now, because I'm doing that direct substitution, I don't need to put that limit out in front anymore because we are taking the limit, or trying to at least. But when we do that, with a little bit of simplifying, we notice that we'll have a 2 minus 2 in the numerator and -1 plus 1 in the denominator, which gives us a 0 divided by 0. Normally when we divide by 0, we say that it's undefined, but earlier in the course we said that this is something special. This is what's called an indeterminate form. Maybe there's an answer, maybe there's not. And what we did is we had a property that says, you know what, we can change how this limit looks. We are allowed to factor our expression up in the numerator. And since I have not taken the limit, I write that notation out in front. And I could do it again. I can do another factoring as x approaches -1 of 2 times x plus 1 and x minus 1. And in the denominator, we still have our x plus 1. There was a property in those limits that said, hey, if you've got this and you can factor a common expression out, the limit of the factored expression will be the same as the limit as the actual expression, except for maybe at that one point. But it was okay because that one point, we're not concerned with what the value is at that point, we're concerned with what's around it. So now we get to this point, and we see that common factor canceled out, and now we can do a direct substitution, where I've got 2 times -1 minus 1, or -4. And so we said before that answer actually worked out. We had as I approach -1 as an x value, my y value approaches -4. I'm not saying that 0 divided by 0 is equal to -4. 0 divided by 0 is just something that told us, hey, maybe there's something else that we can do with this. On the other example, as x approaches 0 of e to the 2x minus 1, again, we can try direct substitution. So e to the 2 times 0 minus 1 divided by 0. Already we're dividing by 0, and that's kind of a problem. But if we look at that up top, we've got e to the 0, which will be 1, minus 1 divided by 0, and there's our 0 divided by 0. So that's telling us that we should do something a little bit more. But if we look at that expression, e to the 2x minus 1, that can be factored. It is a difference of squares. It might not be the most obvious, I guess would be the word I'm looking for, obvious form, but it does factor. But we don't get anywhere. And so that's where this is going to come in very handy. And so we're going to look at a rule called L'Hopital's rule. I'll go back up here. L'Hopital's rule. Mathematician who came up with this this little way of attacking these limits. In order to start this, though, we have to be working with what's called an indeterminate form. Now, there's a number of indeterminate forms: 0 divided by 0, infinity divided by infinity. Those are going to be the two cases that we will concern ourselves with in these exercises and in this course. If you move on and take a Calc 2 course, you'll end up running into infinity minus infinity, 0 times infinity, 1 to the infinity power, and 0 to the 0 power. All of those are considered indeterminate forms, but we're not going to be able to actually use L'Hopital's rule unless it is in one of these two forms. If it's in one of these guys, then we'll find some way to manipulate the formula, to rearrange the formula. So here's what L'Hopital's rule tells us. Kind of a long theorem here, but the idea behind it is pretty nice. Let f and g be functions that are differentiable on an open interval from a to b, containing some point c, except possibly at c itself. Remember, when we're solving limits, we don't care what's at c, we only care what's around it. Assuming that g prime of x does not equal 0 for all x in the interval from a to b, except possibly at c itself, if the limit of f of x divided by g of x as x approaches c produces any of the indeterminate forms, then we can take the limit as x approaches c of f of x divided by g of x, and that is going to give the same result as the limit as x approaches c of f prime of x divided by g prime of x, provided that the limit on the right exists or is infinite. So here's what that's saying. If we run into that indeterminate form, we'll take the derivative of the numerator and the derivative of the denominator. One thing to remember that as we're going through this is not a quotient rule. So let's go up and take a look. I'm going to scroll back up to those examples. We already got one of them that had an answer and another one that we couldn't quite get. So let's take the one that we had an answer. We already know that it works out and it factored out very, very nicely. Had that indeterminate form 0 divided by 0. What the theorem is telling us is if we take the limit as x approaches negative 1, take the derivative of the top. 2x squared minus 2, the derivative will be 4x. The derivative of the bottom, x plus 1, the derivative will be 1. Now, after I do that derivative of the top and derivative of the bottom, we're going to try to solve the limit. In this case, I'm going to go right back to that direct substitution. So we'll take 4 times negative 1, and sure enough, we get a negative 4. Kind of good. Now, if it didn't work out to be negative 4, I'd be a little worried. Let's see what happens with the problem that we couldn't get to work. So in this guy, when I take since I already have an indeterminate form as x approaches 0, the derivative of the top, remember the derivative of that exponential will be e to the 2x times the derivative of what was inside, so 2e to the 2x divided by 1. And so now if we can go at it with a direct substitution, if I plug that in there, we'll have 2 times e to the 2 times 0, or 2. And if you go, and what I'd like for you to do is, if you enter in the equation y is equal to e to the 2x minus 1 divided by x, enter that in on a graphing calculator, and take a look at the picture and see what do all the y values approach as you approach 0. What I'd like for you to do now, there are 6 problems here. And as you go through each one of them, we're going to solve that limit. And you'll notice that some of them will approach specific values. Some of them will approach infinity or negative infinity, and we'll work with a couple of those types. Go ahead and pause the screen, copy down the problems, and see if you can solve these limits by using L'Hopital's rule, if the indeterminate form exists. Now, be careful. Not all of them are going to use L'Hopital's rule. Maybe you can solve the limit like you normally would, or maybe you'll find something that doesn't work, period. But I'll let you go ahead and pause it, give yourself a chance to work through it, and then you can go ahead and continue the video. I'll have solutions to the problems. The first 2 are actually ones that you should maybe recognize. To be honest, I doubt that you do remember them, but they were back in chapter 1 when we first did the limits. We said these are the limits that you have to remember. When you plug in 0 to begin with on the first one, the sign of 0 is 0, and as x approaches 0, you'll have 0. So 0 divided by 0, you got an indeterminate form. If we take L'Hopital's rule, the derivative of the top will be cosine of x. The derivative of the bottom is 1. Direct substitution, the cosine of 0 is 1, which is what we said the answer was to begin with in the first place. The thing to remember here, and I mentioned this earlier, I am not saying that 0 divided by 0 is equal to 1. 0 divided by 0 is telling you that's indeterminate. Find something else that you can do. As x approaches 0, of 1 minus the cosine of x divided by x. 1 minus 1 divided by 0. There is your indeterminate form, 0 divided by 0. So by L'Hopital, x approaches 0. Derivative of the top will have a positive sine of x divided by 1. Plug it in, do the direct substitution. We'll have the sine of 0, and the sine of 0 is 0, which is what we said back in chapter 1, that 1 minus the cosine of x divided by x as x approaches 0 was 0. As you approach infinity on the natural log of x divided by x, this is a different form. That's that infinity divided by infinity. So if we try our L'Hopital's rule, as x approaches infinity, the derivative of the top will be 1 over x. The derivative of the bottom is 1. Now this one, I'm not going to do a direct substitution with infinity because you can't plug that in there. But as the denominator gets huge, 1 over x, the value of that fraction approaches 0. So in this case, as you approach infinity, you approach 0. This one, when you plug in negative infinity up top, now please forgive me, I'm not actually plugging in negative infinity, but we're letting that get very, very large. So negative infinity squared and negative infinity. So up top we will have, let's see, negative infinity squared, that's going to be huge. E to the negative infinity, oh, excuse me, positive infinity, will also go to infinity. All right. So that is going to be something that we can use with our L'Hopital's rule. So I'll have the limit as x approaches negative infinity. The derivative of the top will be 2x divided by the derivative of the bottom, e to the negative x. As you approach negative infinity, up top, we end up with our negative infinity again. And in the denominator, we already saw that e to the negative infinity approached infinity. So on the bottom, I get a negative infinity. The nice thing about L'Hopital's rule says that if it works, if it happens once, there's no saying that we have to stop. So we'll do it again. We'll take the limit as x approaches negative infinity, and the derivative of the top, in this case, your top was the 2x, the derivative will be 2. The derivative of the bottom turns back to an e to the positive e to the negative x. When you let x approach negative infinity, you'll have negative large numbers, which turn to positive, and very large numbers in the denominator. Well, the top remains a constant, will be 0. And I believe I have the same problem copied here. Let me go up and check and make sure. I think I should have one of them that's a... Nope, I did the same one in there. Tell you what, why don't you go ahead and try this one with a positive infinity. We'll make this one go to positive infinity. Sorry about that. Didn't realize that I had the same problem in there. If you try to let this approach a positive infinity, up top, we're going to have that positive infinity. On the bottom, e to the negative infinity. That's a little different. E to the negative infinity. This actually approaches 0. If you think of the graph y is equal to e to the negative x, that sketch will look like so, and as you approach infinity, you'll approach 0. Now, infinity divided by 0 is not an indeterminate form, so I'm not going to do L'Hopital's rule. What I'll do is I'll look back at that problem and say, oh, I've got the limit as x approaches infinity of x squared times e to the x, which means I actually got infinity times infinity, which will be infinity, where the limit does not exist. And the last one, as you approach infinity. Now this one kind of looks like the one that we just did. Still, I got that negative infinity there. When we do a direct substitution, we'll have e to the negative infinity times the square root of infinity. Well, e to the negative infinity, as you approach negative infinity, y equals e to the x, excuse me, e to the negative x, as you approach infinity, will be 0 times infinity. And in your list, that is an indeterminate form. But we can't do L'Hopital's rule with this because that's not that. There is no numerator, there is no denominator. So we take a look at the problem and say, okay, well, is there any way that we could rearrange it? And it just so happens that e to the negative x could be rewritten as e to the x on the denominator. So the square root of x divided by e to the x. And as you let x approach infinity, the square root of a really, really large number will approach a really, really large number. And e to the x, as x approaches infinity, will also approach a really, really large number. And there is our indeterminate form. L'Hopital's rule. Derivative of the top, 1 over 2 square roots of x divided by itself, e to the x. And, you know, I don't like fractions in my fractions. So that's 1 divided by 2 square roots of x times e to the x. And as x approaches infinity, that denominator will get larger and larger and larger. Therefore, your fraction gets smaller and smaller and smaller, so small it will be practically nothing. Hope those went out okay. We'll take a look at a couple more examples of L'Hopital's rule and where that comes up. But that's the idea.